Alright guys, in this video we will take a look at the multiple linear regression. So multiple, that's the main topic, and we're going to look at how to use the multiple independent variables to make prediction about the dependent variable y. You can also write it as MLR. Abbreviation for this is MLR. Okay, and first of all, let's look at the overall model. So the multiple regression model here, we are using for the population. So this is about the population. So predicted y value, yi represents predicted y value in the entire population equal to beta 0, that's y-intercept. Beta 0 is always the y-intercept. Beta 1, beta 2, beta 3, all the way to beta k. That represents the slope for each independent variables. So here we have two or more independent variables. And each independent variable will have a corresponding slope, right? So beta 1 represents slope for independent variable number 1. Okay, and then beta 2 represents slope for number 2, right? For the second independent variable, slope for second independent variable. And beta k represents the slope for kth independent variable. And then here we have error term, random error. So that's basically a multiple linear regression model with k independent variables. So basically, you can use as many independent variables as you wish, as long as those independent variables are useful and effective. Now, if you look at the sample one, right? So y has here represented a sample this is in the sample setting. So this is predicted y values in a given sample. B0 represents estimated y-intercept. B1 is estimated slope for independent variable number 1. B2 is the slope for independent variable number 2. Bk is the slope for the independent variable number k. So in this chapter, we're going to mainly focus on Excel and use Excel to get the regression slope, coefficients, and other regression summary measures. Okay. So in another video, I'm going to show you guys how to get Excel outputs by using the data analysis tools. Okay, so basically, in order to get to the population regression model, we need to have a sample, meaning you create a survey and collect data from your from the population. That will go from there. If you look at two variable model, so this is two independent variable number 1, x1, independent variable number 2, x2. So basically, that will create 3 dimensions. Right? If you look at it, because x1, both independent variables move in different directions. So in that case, we come up with this 3-dimensional animation of this regression model, because independent variable number 1 moving in this direction, independent variable number 2 moving in this direction, it does shift the direction of the dependent variable y. So obviously it becomes a little bit more complicated. And also, when we add in more independent variables, then it becomes more dimensional. So the dimension changes. It becomes much more and more sophisticated. So this is basically an analogy of the multiple linear regression with the 2 independent variables. And let's look at example. Let's say with the two independent variables. Okay. Let's say a distributor of frozen dessert pies, right, wants to evaluate factors having influence on demand, or like having influence on the sales of the pie. So here the dependent variable is a pie sales, okay, unit per week, right? That's a unit. An independent variable we have two. Independent variable number one is price. So price have impact on the pie sales, right? And also second independent variable is advertising spending, and the unit is in $100. Right? So unit is 100. So 1 unit of advertising spending, meaning they are spending $100 in advertising. So the data was collected for 15 weeks, meaning the sample size equals 15. Okay. Now let's look at the data set itself, right? So we have week 1 all the way to week 15, the pie sales with the corresponding price and then advertising spending. And if you look at the first unit here, week 1 here, 3.3 units of advertising spending, meaning the owner spent $330 on advertising spending. Okay, so this is kind of the important. Right? So spend $330 because of units they're using for advertising spending. So the multiple regression equation we're looking at is predicted sales equal to B0 plus B1 times the price times adding B2 times the advertising spending. And we'll try to figure out B0, B1, and B2. That's the main thing. And once you copy the data, put it into the Excel, we'll be able to get the, so follow this direction here. First of all, data analysis, and then we're going to get a regression. So we will generate all the Excel outputs, and then try to measure the goodness of fit, meaning goodness of fit is basically saying, is the model useful, and measure the effectiveness of the model. Measures the effectiveness of the model. Of the multiple linear regression model we are using here. We'll get to detailed analysis in a second. So first of all, let's look at Excel outputs. So first of all, we get regression statistics, meaning R squared, adjusted R squared, standard error, observations. Now we're going to have ANOVA outputs right in the middle. And ANOVA output gives us the overall effectiveness or goodness of fit of our regression model. And the third part is the coefficient, right? And also the standard error, t-statistics, p-values, and a confidence interval, 95% confidence interval. So here, intercept here is B0, right? So B0 equal to 306.52619. And then the B1, the slope for the independent variable price is going to be negative 24.97509. And B2, the slope for the advertising spending, which is 74.13096. And notice that here B1 is negative, meaning when you increase the price of the pie by $1 by 1 unit, then the sales will go down by 24.975 units. And similarly, for advertising spending, if you increase the advertising spending by 1 unit, which is $100, then the sales of the pie will go up by 74.13096 units. And basically, based on these three numbers, we can come up with a regression model. So this is our multiple linear regression model. So the predicted sales equal to 306.526 B0 minus B1, which is 24.975 times the price plus 74.131 times advertising spending. Right? That's B2. All right, so basically we have this multiple linear regression model, and then we're going to look at each individual element one by one in a second. So first of all, let's just quickly give an overall idea about the slope. Okay, so if you look at the B1 here, so B1 equal to 24.975. So what this saying is if the price of the pie, the price increase is increased by 1 unit, meaning $1, then this, on average, the sales will go down or decrease by 24.975 pi. Per week, holding the price, holding the advertising spending constant. Okay, keeping the advertising spending, constant. So that's the interpretation of the B1. So B2 is 74.131. So meaning if the price, if advertising spending is increased by 1 unit, which is $100, and on average the sales of the pie will go up by 74.131 pies per week, holding the price constant, meaning we do not change the price of the pie. And that's basically how you interpret the B0 and B1. And then here there's the B1 and B2, right? And then B0 is 306.526, meaning that's happening when the price, right, meaning x1 equals 0, x2 equals 0, and meaning the price of the pie equals 0, that is not realistic. So we do not have a realistic interpretation of the B0, right? No real meaning. Because the price of pi cannot be 0. Okay. And then since we have the multiple linear regression model, we can use the model to make prediction, right? That's one of the useful features of the regression model. So let's predict sales for a week in which the selling price is $5.50 and advertising spending is $350. $350, you gotta divide that by $100 to get 3.5 units. So advertising spending should be 3.5. That's why you see 3.5 here. So basically you replace price with $5.50, advertising spending with 3.5, then we're gonna get a predicted sales, right? So 306.526 minus 24.975 times 5.5, adding 74.131, multiplied by 3.5, we end up with 428.62. So here the unit for the advertising spending, that's important. You wouldn't put in $350 directly. You have to convert to the corresponding unit before you can plug into the regression model to get a predicted sale. Okay, now R square, right? That's the coefficient of the multiple determination. It's called CMD. Using abbreviation, it's called CMD, coefficient of the multiple denomination, using R square to measure that. So basically it reports the percentage of total variation in Y explained by all the independent variable X putting all together. Okay. So here R square is a regression sum of the square divided by total sum of the square. Regression sum of the square, total sum of the square. So we can easily find that. So regression sum of the square is this number. This is SSR. Goes here, and then total sum of the square is this one. It goes here. And we divide those two numbers, we get a R squared. So in this case, R squared is 0.52148. And then what this tells us is that 52.1% of the variations in the pie sale is explained by the variations in price and advertising spending. So the model is explained by those two independent variables with a 52.1% of effectiveness. And that's how we interpret R squared. And also, an interesting phenomenon is R squared always increases when we add a new independent variable x. So that means if you, right here we have only two independent variables. When we add in the third independent variable, then R squared go up. But it doesn't necessarily means the third independent variable is useful or effective. So this could be a disadvantage when comparing different models, right? So that's why we get to compensate these negative effects. So when we add in a new independent variable, we are losing a degree of freedom, and also the newly added independent variable may not be effective or useful to predict, to add to the explanatory power to offset the loss of the one degree of freedom. So what the mathematician is doing is by introducing a new term called adjusted R squared. I mean, we are considering the sample size also of the number of independent variables being used in our regression model. So here R squared, adjusted R squared, this one is called adjusted R squared. It's equal to 1 minus square bracket, open parentheses, 1 minus R squared, close parentheses, times n minus 1 as numerator divided by n minus k minus 1. So here, since n represents the sample size, k represents the number of independent variables. So we are taking into the consideration of the sample size, also the number of independent variables utilized in the regression model. So adjusted R squared penalize excessive use of the unimportant independent variables, meaning if you are adding a useless independent variable, then adjusted R squared will go down. And also it's always going to be smaller than R squared, okay, to compensate the increase in R squared. Also, it's very useful, right? Matter of fact, it's very useful in comparing different models, especially different models using different amount of independent variables. So just R squared help us identify which model is a better model or which model is more effective. Okay, so now if you look at this, so just the R squared, find the formula from the previous slide, we can get this adjusted R squared. And you can also apply the formula to calculate this adjusted R squared. There's no difference. So in this case, adjusted R squared tells us 44.2% of the variation in pie sale is explained by the variation in the price and advertising spending, taking into account the sample size and also the number of independent variables used in the regression model. As you can see, adjusted R squared is smaller, right? This is smaller compared to R squared. Okay. And that's how we interpret adjusted R squared. And also, you see in the middle, there's ANOVA output. So ANOVA output is used to measure the overall model, right? So if we're using F-test for the overall significance of model, meaning whether there's a linear relationship between the dependent variable y and then all the independent variable x. Okay. So basically, we try to figure out whether there's a linear relationship between all the x variables and then the y variables. Okay. And we're using f-test, f-statistics. So hypothesis here is HO. Now hypothesis is beta 1 equal beta 2 equal to beta 3 all the way to beta k. If all slope are 0, meaning there's no linear relationships, right? And if at least one of the beta is not 0, at least one, that means at least one independent variable have impact or affects the y, the dependent variable. Okay. So that's basically the ANOVA output, what ANOVA output tells us. So the test statistics, we are using f value equals mean of square regression over mean of square error, and equal to mean of square regression equal to sum of square regression over degree of freedom, right? Degree of freedom is k. Okay, and then mean of square error equal to sum of square error over degree of freedom, which is n minus k minus 1. So the k and n minus k minus 1, that's the degree of freedom. So that's overall f-test. Now if you look at this right here, the outputs here, you're going to see for the regression, the degree of freedom is 2. We have 2 independent variables. So sum of the square regression divided by degree of freedom, we get a mean of square regression. So basically dividing those two numbers. And also sum of the square residual is 227,033 and then 306. Degree of freedom of 12, and then divide those two numbers, we have 2,252.776. And then the quotient of these two numbers, mean of square regression over mean of square residual or mean of square error, residual is error, it's equal to f values, okay, 6.53861. And the probability associated with that is 0.01201. So this is the p-value we're talking about. And again, p-value is less than alpha. Right? It's definitely less than alpha. So reject HO. Meaning there's a linear relationship between the dependent variable y and then all the independent variable x. So that's how we interpret the overall ANOVA outputs. Now again, so applying to that pi-cell example, HO, so f-test for the overall model, HO is beta 1 equal beta 2 equal 0, and H1 is at least one of the beta is not 0, or beta 1 and beta 2 cannot be both 0. So alpha equal 0.05, degree of freedom equal to 2, and degree of freedom 1 equal to 2, degree of freedom 2 equal to 12. Now, once we have all those numbers, we can go to the our Blackboard course. Let me just quickly show you how to find f values here, critical f values. So go to syllabus, textbook, and tables. Scroll down to statistical tables, and you're going to look into the f table. Open it. As you can see, degree of freedom 1 is 2, degree of freedom 2 is 12, and alpha is 0.05. So it's going to be 3.89, right here, 3.89. That's the critical f values. Okay, if you go back to the PowerPoint, it's going to be 3.89. That's the critical f values. So yeah, approximately equal to 3.89. So again, you know that in the table A2, it's always only have 2 decimal places. Table F tables from our Blackboard course. Now we can also find these critical F values in Excel. Right, there's a formula for that. Okay, I guess I can quickly show you how to find that in Excel. So go open Excel. And so you're gonna do F inverse, right? F inverse. Okay, here I'm gonna put area to the left. So 0.05, that's alpha, is located on the right tail. So area to the left will be 0.95. Degree of freedom 1 is 2. Degree of freedom 2 is 12. Close parentheses, you'll be able to find the critical F values. You see here 3.885. That's what you see from the PowerPoint. If you run it to two decimal places, 3.89. So there's no conflict, right? So one more time using this formula called F dot inverse to find the critical F values. And then we are using the area to the left, right? Just like the Z test or FT test, we always using the area to the left. And degree of freedom 1, degree of freedom 2. All right, so that's how we find the critical F value down below here. And as you can see, our test statistic F values fall in the rejection region. Okay, so basically we reject HO. Also, we're using the p-value. P-value is 0.012, right? 1201, which is much smaller than alpha, 0.05. That means we're going to reject HO. Okay. That means reject HO, this is out. So at least one beta is not 0. That means that's evidence. With 95% confidence, we can say that at least one independent variable affects one. Okay. At least one of them. Okay. And then if you look at the individual variables, and we're going to do the t-test for the individual variables. Make sure we want to try to figure out, identify those useful and effective independent variables. Also, it will show that whether or not there's a linear relationship between the individual variable and then the dependent variable one. Okay, so hypothesis is HO is beta I equals 0, H1 is beta I not equal to 0. So we're testing each individual independent variable. Testing each individual one by one independent variable. Using the F test. So right here, beta I not equal to 0, that's no hypothesis. H1 is beta I not equal to 0. Okay, that's alternate hypothesis. So if the beta I not equal to 0, so there's a linear relationship existing between xi and y. So the test statistics using the t-value bi, actually bi minus beta I, but beta I is always 0, right? Beta I is always 0, so that's bi minus 0 over standard deviation of the bi. Okay. So degree of freedom is a sample size minus number of independent variables minus 1. All right. So that's basically how we find the test statistical. And right here, we look at both. So we're gonna testing the independent variable price. If you look at it, the t-score is negative 2.30565, and the corresponding p-value is 0.03979, and this p-value is less than alpha 0.05. That means reject HO, which tells us price with 95% confidence, price is significant, useful. An effective indicator of the pie sales. Useful, effective indicator of pie sales, We also examine the second variable, advertising spending. And if you look at the t-score here, is 2.85478, and the corresponding probability here is 0.01449. And again, that's much smaller than alpha. So you can also say that that's a linear relationship with 95% confidence. That's a linear relationship between the advertising spending and also the pie sales. So indeed, there is a linear relationship. I'll just show you different ways of interpreting the result to help you understand this better. Okay. Between advertising spending and pie sales. Okay, and then so we just look into both. Right? So if you want to go with the critical value, critical region method, then we need to know the alpha. We need to know degree of freedom. In this case, it's n minus k minus 1, which is 12. Alpha is 0.05. So critical t-score here, because it's a two-tailed test. This is a two-tailed test. So alpha is evenly spread over both tails. So each tail get half of alpha, 0.025. Then we can utilize that to find out the critical t-scores from either from the Excel or from the table. Yeah, so let me quickly show you how to get that. Okay, so if you want to look it up in a t-table from our Blackboard course. So one more time, we're going to go to t-tables. Just go back a little bit. Open the t-tables. Open here. And so the degree of freedom is 12. Okay, and then the area in two tails is 0.05. And you're going to have intercept 12.1. Okay, so it's 2.179. 2.179 has positive critical z-score, and the negative one will be the opposite. 2.179 right here. If we go back to our PowerPoint, 2.179, right? This is approximately 2.179. On the right hand side is approximately 2.179. We can also use the Excel to find these critical t-scores. So one more time, I'm going to go to Excel and show you how to get that. So we're going to do t inverse. Open parentheses. So on the critical t-score on the left tail with area 0.025, degree of freedom 12. Close that. So we get a critical t-score here, 2.1788. If you run it to 3 decimal, it will be negative 2.179. And then the one on the right is equal to t dot inverse, open parentheses. Now the area all the way to the left is 1 minus 0.025, and degree of freedom 12. Okay. Now you're going to get a similar number, right? Actually, opposite number. Okay. When the 3 decimal place, that's exactly what we see from the t-table. That's how we find these critical t-scores. Both in the table, also using the Excel. So as you can see, both numbers fall in the rejection region, and this number goes here, right, fall in the rejection region. And this number fall in the right hand side rejection region. So we reject HO for both variables. That means that evident both price and advertising spending have a significant impact on the pie sales at the 0.05 level of significance. So that's what we get from this t-test. So both price and then advertising spending are important independent variables to predict the pie sales. And then also let's look at how we construct the confidence interval for the population slope beta I. Right? So let's say for this price, so we get B1. So here the B1 is 24, right? So we're increasing BI with a negative 24.975, which is this. And we find the critical t-score either from the Excel or from the t-table. And standard deviation of the B1 will be this 10.83213. It goes here, and critical t-score goes here, and B1 goes here. And that's basically how we construct 95% confidence interval for the independent variable price on the pie sales. And then the interval turned out to be this. So you get this particular interval. As you can see, this is fairly, so this interval does not contain zero. That means another way of saying this is that pie and the price of the pie actually have a significant impact on the pie sales. Okay, so put in a simple language is basically saying when the price of the pie goes up 1 unit or $1, then the pie sales will go down, will decrease between 1.37 to 48.58 pies per week on average. So this price of the pie does have negative impact, right, on the pie sales. And that makes sense. In most merchandise are the two items. When the price go up, sales go down. And you can also analyze the advertising spending using similar procedures. And if the advertising spending go up by 1 unit, like $100, then the pie sale will go up between 17.55 to 130.71 units per week. So that's how that goes. And that's how we interpret the confidence interval here. So basically, we went over every single element, useful element in the Excel output. Now, most of the time, we're dealing with the quantitative independent variables. But in a realistic or real life scenarios, we sometimes get to deal with qualitative independent variables, meaning categorical data. Okay. So we may have to deal with it like gender, or race, or like a state, or schooling categories. A lot of categorical data or qualitative independent variables. And in this case, we just have to code it. So there's a coding involved here. You need to do coding. It could be done in Excel. I'll show you in the next video when we do the Excel demonstration. So we call this categorical variable, independent variable, as a dummy variable. So a dummy variable is a categorical independent variables with minimal 2 levels, like let's say in the multiple choice answers, yes or no, right? On and off, male, females, it's like gender, and we just code it as 0, 1, right? If one of them is 0, the other one will be 1. Okay. And regression intercepts are different if the variable is significant. And for more than 2 levels, then the number of the dummy variable needed is, let's say, three levels, we're going to use -1, 0, and 1, or something like that, to represent each level or each categorical variable. Okay. And so, for example, like this one, right? So this is about income related to years of post-secondary school and also gender, right? So male, females. So we are coding male as a 0, then female must be 1, right? And so male, female, 2 levels, so 0, 1 to code it. And then once we code the categorical data, categorical independent variable, we call that dummy variable. Then we can use the coding column to come up with the Excel outputs in Excel. And that's actually the most important thing, because Excel wouldn't recognize this categorical data. This is not okay. Excel won't take this categorical data, and then it will cause problems when we get a regression model and also the Excel outputs. So that's why we get a coding. So for example, let's say we have a still dummy variable example with 2 levels and 1 continuous variable. So for example, we want to predict pie sales using the independent variable number 1 price, and the second independent variable is the holiday, whether if there's a holiday occurring during the week and there wasn't a holiday during that week. So overall speaking, there's a holiday during the week, then the sales usually it's better, right? The sales is bigger compared to the week without a holiday. So we are coding with a holiday using 1, right? Without a holiday using 0. That sort of makes sense. And because holiday does have a positive impact on the pie sales, that's why with a holiday it becomes 1. Without holiday it becomes 0. And we look at the net effect of the holiday, like dummy variables in this case. With a holiday, you see, then B2, right, becomes 1. So we have this net impact here, which is increment of B2 units, meaning the pie sales will go up by B2 units with a holiday in a given week. And then without the holiday case, then we don't have the B2, meaning the pie sale will not go up, right? Yeah, so basically, holiday, the y-intercept is B0 plus B2, right? So it actually, so this dummy variable just gives us a boost to the y-intercept, meaning if there's a holiday, then the y-intercept go up by B2 units. If there's no holiday, then y-intercept stays the same. So here, HO now hypothesis beta 2 equals 0 is rejected, and the holiday have a significant impact on pie sales. And in the most case, that's true. Okay. So for example, let's say we have this regression model right here. So you get a predicted sales equal to predicted sales, right? Equal to 300 minus 30, which is the slope for B1, slope for the price, and also slope for the holidays is 15. So with the holiday, then this becomes 1, right? With the holiday, x2 is 1. And without a holiday, x2 equals 0. Yeah, so that's basically what happens here. So B2 equals 15. That means on average, sales will go up by 15 units, meaning go up by 15 pies if there's a holiday occurring in that week compared to without a holiday. Holding the price of the pie constant, right? Meaning we're not changing the price of the pie, holding the price of the pie constant. In the next video, I'm going to show you guys how to run analysis and how to interpret some Excel outputs using Excel. Okay.